So the basis of every good 3D printing result is, of course, the material that is used. And you know that DMG has been successfully manufacturing dental materials for more than 50 years. And of course, we also use this expertise when it comes to developing high-quality resins for 3D printing. And this will be the topic of our next presentation. Our speakers, Dr. Jens Träger and Fabian Oberhofer, will shed light on the different indication areas and provide information on the chemical background underlying the material properties. Dr. Jens Träger is a doctor of chemistry and head of the Digital Application Center at DMG, so he himself was significantly involved in the development and validation of the resins. Our second speaker, Fabian Oberhofer, is a product manager for the digital portfolio at DMG as well, and he will be focusing on the user's point of view. Yeah, and don't forget, both of them will also be available to answer your questions after their presentation. So have fun with the next lecture.
Welcome to our presentation about our DentaMile resins, which are called LuxaPrint. Our lecture today is called From Established Expertise to 3D Printing. My name is Fabian Oberhofer. This is my colleague, Dr. Jens Träger. I had a training as a dental technician in Kassel, and afterwards I made my bachelor degree in dental technology in Osnabrück at the University of Applied Sciences. After this, I came to DMG, and from then on, I worked as a product manager, digital solutions. So in that role, I'm responsible for our digital material portfolio, which is our LuxaPrint resin portfolio.
Welcome also from my side, and thank you for having me. I'd like to quickly introduce myself. Jens Träger, my name. I have a background in science and a doctorate degree in biophysical chemistry. I'm with DMG and DDE for more than a decade now in different R&D roles, and at present at DDE I'm responsible for the Digital Application Center, where we look into the whole digital manufacturing workflow and make sure that materials, devices, printers all interact together well.
Okay, so let's start right now with our resins, LuxaPrint, which are part of our DMG DentaMile principle. You probably already heard something about our hardware and our software DentaMile Connect prior to this presentation, and now we will focus on our resins. These are the bottles of our resins, which come in different variations. We offer some different materials for different indications, and I will go now into them. We offer LuxaPrint tray for your custom impression trays. We also offer a material for surgical guides, which is autoclavable and is called LuxaPrint Ortho. The next material we offer is LuxaPrint Ortho Plus, and this material is suitable for all kind of bite splints, and we will have a closer look at this material later on. Next material is LuxaPrint Cast, which is, like the name already said, suitable for all kind of castable structures like partial frameworks or crowns and bridges. We offer LuxaPrint Model for, of course, models in two different colors. It comes in beige and in gray. LuxaPrint Gingiva for flexible gingival masks for your model work. LuxaPrint Ortho Flex, which is for some types of flexible splints, and we will also have a closer look at this material. And last but definitely not least, LuxaPrint Pro CB, which is suitable for crowns and bridges, and we will have a closer look at this material as special with a little live demo afterwards. All these materials come in two different wavelengths, which are 385 nanometers and 405 nanometers. And as you probably already heard, our system, our validated system, works with 385 nanometers. And why we do so, Dr. Jens Träger will now tell you.
Exactly. Before we go into the details of the various materials, I'd like to make some general remarks. As Fabian already said, our 3D Max and 3D Light printer both use a wavelength of 385 nanometers. And also we try to offer some of our materials also suitable for 4 or 5 nanometers. We believe that 385 is the preferred wavelength for dental 3D printing, and I like to explain why that is so. If we look at the spectrum of electromagnetic radiation, we see a very broad range from radio wavelengths, microwaves, up to very short wavelengths like X-rays or gamma rays. And the part of the spectrum that is visible to the human eye is actually a very tiny fraction between about 400 and about 700 nanometers, whereas 400 nanometers is violet color and 700 nanometers is red colored light. And what is important to know is that the human eye is not as sensitive to every wavelength alike. The most sensitivity is in the green yellowish wavelength range, and the sensitivity drops towards the edges of the visible spectrum, so to say towards violet and red. And what does this mean now for 3D printing? What we see here are the absorption spectra of materials optimized for 385 nanometers, which is a blue curve, and a material optimized for 4 or 5 nanometers, which is a violet curve. At a first glance, it seems they are very much different, but we need to take a closer look at first to the wavelengths the printer uses, which is 385 and 4 or 5 nanometers. And if we look at the 385 nanometers, we see that at 4 or 5 the absorption is very low of the material, making it not suitable for irradiation with 4 or 5 nanometers. So we need to bring that absorption up at 4 or 5 nanometers if we want to have a material suitable for that wavelength, and therefore certain additives are needed. And yeah, that gives very much different spectrum. But what it actually does, it brings the absorption up here at 4 or 5 nanometers to get a nice printable material. But there's one drawback we can see if we look more into detail and zoom into the wavelength range in the order of 400, 410, 420 nanometers. We remember that this is a range where the human eye is still able to perceive color. And the absorption of our 385 nanometer material is remarkably less than that of the 4 or 5 nanometer material, especially here in the range between 400 and 410 nanometers. And what this means is that the 4 or 5 nanometer optimized material absorbs or extracts more blue light out of the visible spectrum than the 385 nanometer material does. And what happens is that we see the complementary color of blue, which is yellow. And to give or to bring that physics we see here back to the practice for the user and the customer, I have prepared a photo of two splints. One is a 385 nanometer material, which is LuxaPrint Ortho Plus 385. And on the left-hand side, there's a 405 nanometer material. And we see that the left side is remarkably more yellowish in color. This is very pregnant to be seen in clear materials like we have them for the bite splints, but this will also be an issue for materials that need to be very exact and stable in color, and therefore we prefer 385 nanometers for the best results in dental 3D printing. And now Fabian will give you some more details and insights into our LuxaPrint Ortho Plus material.
Right, because of course we use all these technology advantages to bring them together and put them into our product to offer you the best product you can get for your bite splints. And this is LuxaPrint Ortho Plus. And as you can see on the picture on the right side, it is really transparent and there's not a glimpse of yellow in it. This material is suitable for all kind of splints in a 3D printing process. It's also suitable for the printing of orthodontic appliances. Which is important is, or what is important is that this material is certified as a Class 2A medical device. So it is also suitable to be to stay in the mouth for a longer time. We already said this material is really clearly transparent, and it's really clear, not yellowish or anything like that. And we will show this to you in another picture after this. What's also really important for a printed splint, but also for a common splint, is the fitting. And we can achieve a really exact fitting of a printed splint out of LuxaPrint Ortho Plus. So you will always have the highest comfort for your patient if he wears a splint out of this material. And what is also important is that even though it's a hard splint material, it is not brittle and won't fracture into many little pieces when the patient has this kind of splint in his mouth. On this picture you can see the really clear transparency without any color in it, and you can see how easy it is to polish it and to get a nice shiny finish on the surface of this splint. And the material gets even more transparent when it comes into contact with saliva. So yeah, this is for really high aesthetics. On this picture, where you can see a crosscut through a printed splint, you can see how good we achieve this exact fitting of the splint. In all areas where it needs to be in direct contact to the tooth, the splint is in direct contact. So you will always have a perfect fitting splint, which won't break due to some kind of misfitting. And how we achieve this kind of perfect fit and all these material behaviors, Dr. Jens Träger will now tell you.
Yeah, thank you very much, Fabian, for that insights. And of course, we go much further than looking at the application of the material. We also do various tests, and yeah, one exemplary picture I have here, which is a look into our 3D wash cleansing device. And on the left-hand side picture, you see two splints or orthodontic appliances. And on the right side, you see some maybe rather strange objects, which are test bodies used to test properties like bending strength, tear strength, color, and some others which I will explain in the further course of this talk. At this point, what is important for me to say is that we apply exactly the same process to our test specimens as we do to the dental objects we or our customers and users would produce. So all the results we get are an exact representation of the workflow. So printing, cleaning, post-curing, all other steps are the same for the test specimens as they are for the real dental parts. And one of such tests is bending strength. We see here the device to measure that property attached to a computer, and it records the force and the amount of travel needed to bend and eventually break such a test specimen, which we see here. Of course, the test will commence until the specimen actually breaks, and we record the so-called flexural strength. We see that the flexural strength of our LuxaPrint Ortho Plus material is about 80 megapascals. And we also see that the flexural strength for the 385 nanometer version is the same as for the 405 nanometer version. We remember that for the 405 nanometer version, we have this issue with a more yellowish color and maybe a not so nice appearance, but in terms of mechanical properties, we still achieve the same high quality of the material regardless of the wavelength version. And in yellow on the right, we see the flexural strength of a conventional product used to vacuum form splints, and this is about the same flexural strength as our 3D printed material. Another value that is generated in the same test along with the flexural strength is a modulus, and the modulus is a number that determines how resistant this material is to deformation under a certain force. So the higher the modulus, the more stiff the material is, and the more or the lower the modulus is, the more flexible and bendable the material is. And we have a modulus of about 2.2 gigapascals for our material here, which is in the same order, about 10% higher than the conventional vacuum form product, so very much comparable. Besides that static mechanical test I was talking about, which exerts a force onto the test body until it eventually breaks, we also look into what happens when applying an alternating force to such a test body, which allows us to see how such a material would behave in the oral cavity when it's subjected to the various biting and chewing forces, which are higher and lower and vary over time. In this test, which looks very similar or basically the same as a 3-point bending test, we apply a force which is varied over time in a sinusoidal way, up and down. and it will bend and release a test specimen a very high number of cycles, which is in the order of 10,000s, 100,000s, and we see in this little video how this would look like in reality. So the specimen is bent up and down, and we see how it behaves under dynamic loading, and of course make sure it won't break early. Another important thing when looking at our materials, besides mechanical properties, is sorption and solubility. So sorption is a property which says how much water is taken up by the object, so by the splint, when brought into the oral cavity, and solubility is how much is leached out of this object. And we see, which is preferable, that we have quite low values here, both in sorption and solubility for our LuxaPrint Ortho Plus. These values are also well below, for example, compared to the limits given in the ISO standard 4049 for polymeric restorative materials. And what we further do in our toxicological department is, of course, not only look at the amount of substances that are leached out of the object, but also do chemical analysis to determine what exactly comes out, and if there is any concern regarding to those substances. Last, I would like to show the results of a stability test where we subjected objects in our in-house material testing department not only to water but also to a popular mouth rinse and cleaning agents for orthodontic appliances and dentures, to see if those agents would degrade the material in any way. And what we see here, both for the Flexural Strength as well as for the module, is that over 1,000 cycles there's no degradation in mechanical properties. And on the right-hand side bar, we see an accelerated aging test standing for 1 year of time. And we also see that there's no degradation in mechanical values over time. In fact, in this experiment, the Flexural Strength even is higher after 1 year than the initial value. And now Fabian will continue with a material that is different from LuxaPrint Ortho Plus in a way that it's more soft and flexible.
Yeah, exactly. Now we heard enough about some kind of hard material for bite splints, but we also offer a material for flexible splints. And as you can see in this picture, this material is also really transparent and isn't yellow in any kind. This material is suitable for flexible splints, soft splints, and it's certified as a Class 1 medical device. You can use this material for bleaching splints or bleaching trays, and for indirect bonding trays. So you can use it in these two kinds, and for both of these applications it has an optimal elasticity, because it needs to adapt to the gingiva, to have the bleaching gel exactly in the place where it is meant to be, and so it needs to be a little more elastic and flexible than our hard splint material LuxaPrint Ortho Plus. Even though this material is flexible, it is really tear resistant, so it won't break that easy. And as you could see in the picture before, it has a near natural transparency, which is in fact a little more challenging for these kind of flexible materials. But we did it. And last but not least, this material is easy to clean. And when I say easy to clean, I refer to the use as a bleaching tray. If the patient uses this kind of splint for his home bleaching and use this splint more than one time, he needs to clean it after the usage from the bleaching gel, and this is really easy to do just with a common toothbrush.
Yeah, and here on this slide we can see how flexible the material actually is. So we can quite easily bend such a splint all the way until the ends touch each other. And at this point, I would like to use the occasion to explain one of the challenges we faced when making such a material. You maybe heard the previous talk about devices, so I won't go into too much detail of the printers, but what is important to know here is that we have the liquid resin in our wet, and we cure the object with our light source layer by layer, stacking layer by layer to the build platform and onto each other until we have our final object. And that also means that we have to tear every layer from the bottom of the wet to lift the object and to cure the next layer. And this gets more and more challenging the softer the material gets, because we do not want to tear the object apart, of course, and we do not want to have irreversible deformation in the object, which would lead to imprecise objects which deteriorate from the data set you actually wanted to print. So yeah, one challenge of which I'm glad we did overcome is that we get also out of this a very soft and flexible material very accurate objects and good printing process without torn or deformed objects. And now we would like to get from our softest materials to one of our hardest and strongest materials, which is LuxaPrint Pro CB. Fabian.
Right, thank you. Yeah, as you can see in the picture, LuxaPrint Pro CB is suitable for crowns and bridges. But it's not only suitable for crowns and bridges, but it's suitable for inlays, onlays, and veneers as well. So from now on, you can produce your crowns and bridges and so on in a digital workflow, in an additive workflow. You can print them. Of course, this material is certified as a Class 2A medical device, since it is meant to stay in the mouth for a longer time. We offer this material in 5 different colors, so it comes with excellent aesthetics and will be suitable for a broad range of your patients. It has a verified high stability, which is of course necessary if we want a material which can withstand these high chewing forces in the mouth. You can use it not only for temporary restorations, but only for long-term restorations or long-term temporary treatments. Yeah. This material has, of course, and we already heard about biocompatibility, a reliable and confirmed biocompatibility, which is necessary to have a safe medical product for your patient. It comes with a little special product which is called LuxaPrint Finish, and thanks to this product, this material is really easy to finish and to polish, so it will take not that much time to have a really nice looking, shiny and glossy crown or restoration. And what's so special about this material will now be told to you by Jens.
Well, here we see how a crown made of LuxaPrint Pro CB would look like after coming out of the 3D wash. And you can see that there's a white flower-like residue on the surface, and this is due to the fact that we have a real composite material here with containing an inorganic filler. And during the washing process, when resin is removed from the surface, those filler particles will become visible, and that makes up this white powdery layer on the crown. And we developed a LuxaPrint Finish, which is a product that is applied to the surface of the crown or bridge after cleansing it in the 3D wash. And this finisher coats the whole surface and gives a hard, nice and visually appealing surface finish. After applying LuxaPrint Finish, the object is put into the 3D cure to do the post-curing as you would do with any other 3D printed object of any other LuxaPrint material. And during this post-curing process, both the objects and LuxaPrint Finish are hardened together and will make a permanent junction there. There you get, at the end of the process, a very nice object. Of course, you could, if you want to polish it, to get an even better luster if needed. And this material is a patent-pending technology developed here at DMG. And why we chose this workflow with LuxaPrint Finish is shown here. What we see here is a 3D scan of such a finished crown. And we see from this green color and this distribution function here that this object is very accurate in terms of comparison with the digital data that was printed here. We see that the margin is very clear, and also the inside of the crown is very accurate. There are no residues of material left inside, and that is why we do a rather rigorous cleaning in the 3D wash with isopropanol and then apply LuxaPrint Finish. And you can also see that LuxaPrint Finish is not a kind of varnish, so it's not building up a layer that would in the end make the object too big on the outside or too small on the inside cavity. It basically only seals the surface without making the object inaccurate. You could basically avoid this white layer we've seen on the slide before by just wiping off a residual resin with a cloth or a brush or something similar, but you would never know if you have really thoroughly cleaned the object. And it's a rather high risk that residues of resin could stay on the inside of the crown, which is shown in this picture. Red color means that there is a positive difference, so too much material compared to the original digital object to be printed, and this could of course give problems when fitting the crown. So when there's too much material here on the inside, the crown could not properly fit on the tooth stump when trying to cement it. And now Fabian will give you a live demo on the application of LuxaPrint Pro CB and LuxaPrint Finish to show how fast, easy the process is and what nice outcomes we can achieve.
So let's now come to our little live demonstration on how easy it is to apply LuxaPrint Finish to LuxaPrint Pro CB. After the washing process, our crown out of LuxaPrint Pro CB has, as Dr. Jens Träger already told us, this whitish surface. And so now I will remove the crown from the base plate just by removing it with my fingers. And now you can see how this white surface looks like. And now I will apply this LuxaPrint Finish out of this bottle, just one drop on the surface and applying it with my little brush. And all we're looking for now is that every part of the crown, inside and outside, doesn't look white anymore, but has a wet looking surface with LuxaPrint Finish. So I'm also including or applying this LuxaPrint Finish to the inside of the crown. And so this is how it looks now. Usually I just would dry it a little bit with compressed air, but since I do not have compressed air here at our TV studio, I just place it in the 3D cure to cure the material LuxaPrint Finish and LuxaPrint Pro CB together. And this is how the finished LuxaPrint Pro CB crown with applied LuxaPrint Finish looks like when the curing process is finished. So now we do not have any of these white stains on the surface, but we have a nice looking surface, and now it's really easy to polish it, to finish the surface, and it will take only a few moments for you. And this is, just for your comparison, how a polished crown looks like after the finishing of the surface. And I hope you can see it through the camera that the surface is really nice looking and shiny, just like a tooth should look like. Yeah, and that's it from our little live demonstration of how easy it is to use these products together. And now back to our presentation.
Thank you, Fabian, for this nice demo of LuxaPrint Pro CB. And in the last part of our talk, I would like to give you some more insight into the development and validation of 3D printing parameters in our application lab here at DDE. What we see here is a picture of our lab, and of course we do have all the printers we sell and we validate our materials with, like this 3D Max and 3D Lite, and other printers we do validations for, and of course we have the washing and post-curing devices which are not shown in this picture. And in the previous parts of our talk we saw how we do mechanical testing and biocompatibility and various other tests. And now I would like to talk about the development of the parameter itself. As you know, of course, a 3D printed object is built layer by layer. And here we see in this example how 3 respective layers would look like. So this is what the projector would expose in each layer, and these layers are stacked on top of each other, giving the desired object. And if you look into that matter in a more schematic way, we like to take a look on what happens at the bottom of the wet when the last layer is about to be printed and attached to the layers that have previously been built. We need to cure the material in the thickness of the desired layer, and we of course need to make sure that the last layer printed is attached firmly to the layer before, so we get a dense, nice object which is not delaminating or showing any defects. So we want to get a dense, homogeneous object, and therefore we need to make sure that the layers are thoroughly attached onto each other. But on the other hand, what we do not want to do is to cure too much material, especially not in parts of the objects where curing is not desired. So in this example here, we have a cured object part which is right in the process of being printed. That part is already printed, and what we want to do is we want to print a nice round hole in the direction of the stacked layers. And there's uncured material, and now we need to build up the rest of our hole. And what we want to do is we want to cure the final layers in a way that we get our object built up here, and we get our hole, as I said, nice and round. But if we are about to expose our material like here to the light, and we overexpose it, we could end up with a situation like this. So we start to harden into the cavity we actually wanted to create, and we don't get a nice round circle, but we get a deteriorated form like we can see here. And of course, this is what we do not want to have. So we need to adjust the exposure of the material and all the other parameters right to get a proper object. And of course, this is most difficult to be achieved for a clear and transparent material, because light can easily penetrate through this object. Very colored materials are a bit less challenging in that part, and we see here for our LuxaPrint Ortho Plus how a 3D printed object actually looks like. And on the left hand side we see the digital data file we used to print, and as you can see, we have here holes of various sizes which are all printed very accurate, very round, no undesired material left here, and even a hole as small as 1 millimeter in diameter can still be printed. And after looking into the printing process itself and the exposure of the material, of course we do not stop at that point. We do the whole cleaning and post-curing process. Like you see here, we remove the objects, wash them either in the 3D wash or by hand, and we dry them, we do the post-curing, and we do the finishing, like removing support structures or polishing the objects. And then we assess how the object is at the end of the process of our validated workflow, as our users and customers would do in their labs. And yeah, one thing is accuracy. Here is, as an example, a dental model, and we want to have a good fit of the two stumps into the respective cavities. We don't want to be them too loose, and on the other hand, we want to have a good fit. We can see here in this picture that we can achieve a good fit and a high accuracy, but we do not stay at testing this in a sensorical way. We mostly rely on objective data, which we record with a high accuracy 3D scanner, which is shown here. So we take the object that comes out of the process, out of our workflow, and we scan it. We get digital data from this printed object on a micrometer scale and accuracy, and we use the scanned data to compare this data with the data set we initially gave to the printer to create the object. So basically the initial STL file is compared to the scanned data of the object after finishing the whole process. And then we take a look at how big or how small the deviations are. And for example, for a model, we want to have a deviation not exceeding 60 microns on at least 80% of the surface. And you can see an example which we of course would not give out into the market, but just to show what could happen if this has not been done right in terms of parameter development. We have parts that are too big. There's too much material shown in red, and we have this bluish parts where there's not enough material, and we have a deformed object also seen from the histogram here, which is not accurate in terms of the digital data set. And on the right hand side we see a much better object, mostly green, which is inside the tolerance limits. And two more examples I've brought here are from a bite splint on the left hand and from a drilling guide on the right hand side. And in these occlusal surfaces we see the deviation between the scanned object and the initial digital data set or STL file in millimeters, and we can see that we have deviations in the order of 10, 20, maybe sometimes 40 microns, so we can really get high accurate objects. And one thing that actually influences accuracy of 3D printed objects is how they are oriented inside the building envelope. Here are examples of a bite splint printed parallel to the build platform. Build platform is shown in green color here, and at various angles. And yeah, we did test that. We looked into the accuracy and looked into object deformations, and that is why you get recommendations in our application notes, for example, on what orientation would be best and preferred to get the most accurate objects out of your printer. And to conclude that, I use this picture of this old and big tree here to explain and to show what parameter development means in the end. So like the limbs and branches of the trees, also starting from one material, parameter development is a branch process, because if we start from one material, we would need to validate every printer like the 3D Max or other printers we would like to validate, then we would have to validate every layer thickness we are interested in, and for every layer thickness we would have to validate every post-curing device that should be used in the process, like the 3D Cure or another UV box. So this is branched up and up in a bigger way, and we do a lot of work in our lab to grow the tree and to be a good gardener, and a lot of work is or has been done in the parameter development before those parameters and materials are brought out into the market for customers to use. And that gives you, in the end, the security and assurance to have a good results with our validated parameter sets. And now Fabian will, to conclude, show you how we give out information about printing processes out into the market.
Yes, exactly. So we developed a tool to assist you as best as possible in your daily work with our materials, with our whole validated workflow. And what we developed are these application notes Jens already have mentioned. In these application notes, we guide you through your whole workflow for each material. So, for example, for LuxaPrint Ortho Plus, we start with the scanning, so your entrance in the digital workflow, and then afterwards guide you through the whole process, which includes the designing, the printing, the post-processing. And we also give you additional information on how, for example, to position the splints, as Jens already mentioned, and how to achieve highest accuracy, how to boost your productivity, and so on. We give you a lot of advice and hints in these documents. And in this moment, they are available for LuxaPrint Ortho Plus and LuxaPrint Ortho Flex. But we aim to offer you an application note for every single material we offer you as well. So now I can only thank you for joining us today. Thank you, Jens. And I hope you have a great IDS and had a little fun with us today. Could take something home with you, and see you next time.
Thank you for joining us today and listening to our talk. Have a nice and exciting visit to the IDS fair, be it virtual or in person in Cologne, and a nice day.
Yeah, so welcome Fabian, welcome Jens here on stage. And we got some questions in the chat. First is, are the materials also validated for Aziga printers?
Yes, actually most of our materials are validated for Aziga printers. And if you ask this way, you probably own an Aziga printer by yourself, and so you should know how to get these data from the Aziga homepage, so you have the parameters to print with our LuxaPrint materials.
Thanks. In which layer thickness can I print the materials?
Yeah, it depends, and it depends on the material. So basically in most materials we offer 50, 75 and 100 microns. In some cases, like for example LuxaPrint Cast for castable structures, we offer also finer layer thicknesses like 30 microns. If you want to print individual impression trays with LuxaPrint tray, you want higher printing speeds, so we offer also 150 microns.
And there's another one. Are there any deviations of the printed objects from the designed objects?
Oh, that's for you, Jens.
Okay, thanks. Yeah, well, very good question. Deviations are there, but they are quite small. As I tried to show it in the talk, showing the 3D scans, we have deviations in the order of about 60 microns. You need to keep in mind that you have a projector in the DLP printer, which has a pixel matrix like you have on a projector you use for watching movies or watching TV. Of course, our pixels are quite smaller in the DLP printer, but we still have pixels which have a size of about 68 microns. So you have, due to the fact that you need to put a free scale object into that pixel matrix, you have a deviation of plus minus 34 microns, and you have a little bit more deviations, which gives us this 80 micron number in deviation, but you get very high accurate objects.
Mm-hmm. And how time consuming is the validation of a material?
Validation is quite a time and work consuming process. We do basically validation is based on 3 pillars. One is dimensional accuracy, which I commented on in the question before. Second pillar is mechanical properties, which is done by our material testing department. And third pillar is biocompatibility testing. And also 3 have to be checked and have to fulfill all the requirements so that we can finally say it's a validated workflow for a specific material on a specific printer. And of course, that's a requirement to release that parameter to the market. So it's quite a lot of work we do behind the scenes, basically.
Mm-hmm. And you already mentioned biocompatibility, and that's also what the next question is about. How is biocompatibility ensured?
Well, we have a dedicated person here in our company who does a toxicological assessment, and what is done there is to look what kind of leachables, or if there are any leachables that come out of a printed object, and to check what these substances are and in what amount they leach out of the objects, and to assess that all analytically, and do some in vitro tests like with cells to assess things like cytotoxicity or any harmful potential of those leachables, and only if there is no harmful interaction with a human body or with oral tissues, then biocompatibility is granted, and we can go forward with the material and with the material parameter.
Mm-hmm. Yeah, thanks. That was it in terms of questions. Yeah, thanks a lot to both of you.